Okay, so now let's solve these three problems which are about these thermodynamical processes. So the first one, let's read this 15.3. Suppose the initial volume is the same in both an isothermal and an adiabatic process. So that is similar to what we already discussed when we were talking about, I'm going to remind you, when we were talking about these two curves, the isothermal and the adiabatic. We are starting both with the same volume, and well, the problem doesn't say, but let's say they start both with the same volume and same pressure. Okay, all right, so we continue. Initial volume is the same for this isothermal and this adiabatic process, volume and pressure. If the final volumes if the final volume is also the same for both processes, in which process was more work done by the gas? Before we solve this problem, let me tell you about something that remained to tell you about when we obtained this equation. This was the equation that we obtained for work in the case where pressure was constant. So if I would make a plot for this, I would have a case of pressure versus volume. So the scenario is something like this, where I start at this point, certain pressure, let me call it PA, certain volume, let's say VA, and we finish somewhere here, same pressure, but another volume. So that's an example of a situation where this equation would apply, where this equation that work is pressure multiplied by delta V would apply. Okay, what is this equation telling us? That what we are doing is we are getting this value of the pressure, right? This value, and we are multiplying by this value of the delta V. So what we are computing is the area underneath this curve here, correct? So this is to say that work is the area underneath this curve, in this case, this curve for the process. In our case, it's just a flat curve, but we could have more interesting or more elaborated processes where both would be changed, like the pressure and the volume, something like this. And again, if you asked compute the work, well, you would have to find this area underneath this curve. Okay, this would be a more complicated problem, but it's still doable. In this case, we use integrals to solve. All right, all this to now come back to this problem. Okay, so what they are saying is we have two processes, isothermal and adiabatic, both starting with the same pressure and volume. Okay, so similar to that problem that we already discussed before. So let's make our plot here. Both processes are starting here. Same pressure and same volume. Okay, now remember what we discussed. In the isothermal process, the temperature does not change. So we go from this point, let's call it A, to this point B. And again, PA, VA and PB, VB have to be the same value because the temperature is constant. All right? But in the case, so this is our isothermal. But in the case of an adiabatic process, what happens in an adiabatic process? Remember that in an adiabatic process, it happens so fast that we don't exchange heat. In this case, the delta U is equal to minus the work. So the temperature, delta U is related to the change in temperature, so the temperature decreased. So as we said, in an adiabatic process, this curve will end up somewhere below. Now we start both at the same point, but in the adiabatic, we are going to end up in a lower point, this point C here, because the temperature has to drop. So this PC VC will be smaller than the PA VA. okay, because the temperature dropped. Okay, so this is to remind of what we had discussed before, and now comes the question again of this problem. So, in which process was more work done? More work is in the process where we have a bigger area underneath the curve. So bigger area is for the isothermal, right? Because for the adiabatic, it's just this piece here, the work. So more work is done in the isothermal process because we have this larger area, this larger area here underneath the curve. Okay? Okay, let me just discuss one more problem, which is this problem 15.4. This 15.4 is a conceptual problem. It's a problem that gives us a good idea of what an adiabatic process is. I was saying an adiabatic process, something that happens so fast that we don't get the chance to exchange heat. The system doesn't exchange heat. Okay, so what is the example for this adiabatic process? Something that I used to do a lot when I was a child, and I bet many of you did the same kind of game, which is get a rubber band, thin rubber band, and then you touch it with your lips. You touch it with your lips, and then suddenly, boom, you stretch it really quickly. And if you touch it with your lips, you will feel that the rubber band gets a little warmer after expanding. Now, so what are we doing with this rubber band? When you expand it quickly, you stretch it quickly, very quickly, very fast. What it means, well, that you don't give time for the rubber band to exchange heat with the surroundings. So it's an adiabatic kind of process. Okay. Now the question is, why does it get warmer? Why we touch it and we feel this rubber band warmer? If you have never done it, try to do this experiment. Get a rubber band and extend it, and you will feel it warmer. So why? Well, if the process is adiabatic, as we said, we don't exchange heat. Well, if I go to our equation delta U, I don't have the Q in this story. Okay, I don't have the Q, so we don't even need to put it here. Next, what we would put is the term of work. Now the question is it the system that is doing the work, or is it me who is doing work on the system, on the rubber band? It's me, right? I am the one stretching it. So I am doing work on the rubber band, on this system. So this is plus, okay, the work that I'm doing here. So conclusion, delta U in this case is plus the work. So we are adding energy to the system. I'm strong enough to stretch that rubber band. So this explains why the temperature raises. I'm doing the work. The delta U is going to be positive, so the delta T is going to be positive. I'm going to stop here, and I'm going to solve the problem 15.5 in the next video.